We're back again here in our lecture series in Computer Science 455 Software Engineering. Today is 11th of May, Monday. Okay, before the lessons, I would like to remind you about the deadlines that we have set up in our course syllabus. So let me show you that. Okay. Um, we are on the 6th week of classes right here, and we're continuing with the um, chapter 6 systems design. Um, oh, by the way, we're opening up a new chapter, systems design, um, fulfilling design goals. And over here, you'll see that I have asked you to submit to me your revised SRS, revised SPMP, and revised SQIP yesterday, the 10th of May. Going through this, and over this week, I'm going to return to you the final review for the final review of your revised SRS, SPMP, and SQAP. In the lab, we began last week the launching of or the previous week, launching of prototype number 1 development. Last week, we continue our development, and at the 11th of May, we are here on this particular week continuing our development, and next week, the 18th of May, you will deliver your prototype number 1, and QA will begin testing. Okay, so that's the course syllabus of what is due. Would like to remind you that as soon as I approve your SRS, you must show it to your client and get their approval as well. Okay? As I have said in the syllabus, we are going to do the software architecture and design document for this entire week. So 11 to 15, you will come up with your software architecture and design, and this could overlap with coding. And I mentioned before, it is a cyclic overlapping process between designing and coding. So as you are coding, you might discover some issues and improvements to the development, and therefore you want to update your design. And so you fix your design and then continue coding. And that's normal, because you never know till you are coding and finding out issues in your design. So the 18 to 22 is the entire week is devoted to your delivery of the prototypes to the QA. and the QA will be informed that you are ready to be tested. So what they'll do is they'll have access to your repo, and from the repo, they will check whether you have completed all deliverables as defined in your SPMP. That means, do you have the SRS? Do you have the SPMP? Do you have the software architecture and design? Um, and other things, source code are in there. And you should tell the QA team how to compile and how to build the mobile app. So give them instructions. The QA team will perform it and make a build, and then they install the mobile app to a mobile device or an emulator, and from there QA team will test. You are not supposed to give them the executable module of the running mobile app. The QA team will build the mobile app based on your instructions. Of course, if it didn't compile and didn't build, then you failed the test. Okay? So make sure that the instructions are correct and accurate so they can compile and build the mobile app based from your instructions to test the mobile app. They have to build the mobile app from scratch. Okay, that means using your code and other things that you will need to come up with the running executable module. Okay, so that is the week of 18 to 22nd. So you make arrangements that during this period that you are ready for testing. Okay, so if there are any questions, let me know. Um, Let me talk about the software lifecycle that we are following. Remember this diagram that I've shown you on the first week of class. Okay? So here is the software lifecycle we are following. First, client has an idea. We convert, translate that idea into a document that both you and the client understands what the client wants. So we go through several iterations, and when you obtain the software requirement spec and following the agile software development, we don't need the entire specification of the software. You can have a little at a time. That is why it's called iterative and incremental development. We don't need to get the full spec at the beginning. A few will be good initially, and then build from there through incremental developments. So as soon as we know what to develop, the teams will now plan, and the planning is coming from a document called Software Project Management Plan. How do you plan? There are two outputs of the SPMP: the schedule and the amount, the budget for the project. Okay, so this is the plan on what to do using agile methodology. This could be a 4-week sprint, a 3-week sprint, or a 2-week sprint. And every sprint, you produce some functions, and remember, and don't forget the non-functional requirements as well. to include in your milestones. Okay, and once you have the plan, the team is organized, then you come up with the software architecture and design. Just like in a design of a building, we just don't begin building or constructing the building without any plan or design. Similar in software, we just don't begin coding at the start without understanding the different parts of the software, and also what are the design goals. You must consider the design goals, or else what you're building may not fulfill those design goals. And what will happen in the future, you have to, the worst case is to abandon the software project, and it happens in many big projects by software companies. They abandon the, um, the development and begin all over again because the design was wrong. Okay? And then after that, you have the coding part where you have Scrum or XP or micro waterfall, spiral model, whatever you adapt as your software process for coding. That's what you do. And now here is the QA team waiting at the end to test your um, um, prototype or the iteration that you have produced. Okay, so they will decide whether you pass or fail the QA testing. Now, QA will test the um, use case that you have specified in the SRS, whether you fulfilled all use case in the SRS. And each use case may have one or more user interface. So they're going to use the user interface to select test cases to see if your project is working. Okay? So very important role played by the QA team. They also watch the software process that um, you are following. Um, we have verification and validation techniques of unit testing, integration testing, system testing, and regression testing. Are you following that? And they're also gathering metrics. They're also watching whether you are gathering metrics like quality of your code. We measure that by the number of faults per 1,000 lines of code, and the productivity of the team. How many lines of code do you produce per hour? And that would be a very important metric in estimating the time of when you can finish a software project. Okay, and remember, in the SPMP, we have an estimate of when you will finish and an estimate of how much it will cost. Um, how much will it cost the whole project? And as I said, 99.9% of the cost of producing software are the salaries of software engineers and everybody else who are involved in the development. Okay, so it's time and budget. That's the bottom line of the SPMP. And then once the SQAP pass your prototype, it is given to the client, and the client gives you feedback, and from that feedback you go to the next iteration again. So you begin SRS for the next iteration, and you begin the whole cycle again. Okay, that's agile iterative and incremental development. Okay? All right. Um, let's proceed to the um, next. Let me check the previous slide. Yeah, we've done that. So the next slide is the attendance report. Um, Up to this time, I am getting attendance report in the direct channel. I want the attendance report to be posted on the Teams channel because there I can see the exchange of communication among the management team and the team members. I want to see that communication going back and forth during the lab time, 10 to 12 p.m. for the Monday group and for the Wednesday group. Okay, I want to see that because this is online. If I am teaching this on a regular quarter and we are not shut down or locked down, I will be going around the lab watching each team what they do during the lab time. And since the team is there in the lab from 10 to 12, I can observe what's happening in the lab. And sometimes I would listen to the conversations going on in the lab, and sometimes I would join the discussion. Or they will ask me for questions. And that's when I can gauge whether the team is working together. Okay? So I need to see that exchange of communication between all of you in the team during the 10 to 12 p.m. So don't give me the attendance report before the time of 12 p.m. because I want to see, I said, all the communication that is going on from 10 to 12. Don't give me the attendance report earlier than 12 p.m. You understand? The purpose of the attendance report is this is my only window of observing how the team is coming together. And some of you have opted for other communication medium. That's fine. If you like that other communication medium, that's okay. You can do that. But give me what was discussed during the 10 to 12. So give me a summary of what was discussed and who proposed or who is talking about a particular topic in your conversation. I want to see the person who is responsible for producing that idea or questioning an idea. Okay, this is the only way I can see participation. Okay, if I am teaching this in the regular quarter, the best way to teach this course is face to face. Okay, so right now we are experimenting whether this can be done online. Okay, and so this is a tool that I use to substitute for the face-to-face meeting and observation of what each team is doing through the Slack exchange of communication. Understood? Okay. Hope that issue is resolved. Don't send me the attendance report in my direct channel. I want to see that in the Teams channel. Okay, so let's talk about the software architecture and design document. Okay, some of you have already started looking at the software architecture and design document. That's good. You are going ahead of me when discussing this. uh, we don't have a sample template um, for this software architecture and design, but what I have is an outline. Okay? This time, we are not following the IEEE standard because I want to focus on three items in the software architecture and design. Okay? First, I want to see the version number of this document, the project name, who is the management of the team, managers of the team, the PM and the APM, and the software engineers involved here. Now, um, let me um, assign the task for the high-level design. The management team is responsible for that, and the low-level design and detailed design are the responsibility of the software engineers. But all of you can collaborate with each other at any level, so you learn everything, but you are responsible for the entire document. Okay? All right. First, what is the purpose of section 1? What is the purpose of this document? And what is the purpose of this document in maintenance? Now, some of you will probably receive continuing projects from previous, and the software architecture and design is missing. Okay, and that's one of the main reasons why you don't have a sample template, because not everybody follow this part of the software process. Okay, so in maintenance, this is where it is a very high value, because it tells you what is the overall structure or outline of the entire software. I think I gave you an example of you are inheriting a project that is, let us say, maybe 20 to 30,000 lines of code. It's a big project. And you're supposed to maintain it. If the software architecture and design document is missing, then you will have a hard time understanding these 20 to 30,000 lines of code. Okay, the time it takes to understand that source code is going to be wasted in trying to find out what is this module doing, what is that component doing, what is that package doing, and so on and so forth. Now, if you have a software architecture and design, which is in terms of UML diagrams, uh, uh, the design probably will take maybe several, or it could take depending on the size of the project, many pages of drawing, but you are looking at drawings rather than source code. So the level of the understanding of how the software project is working is better understood by looking at graphical symbols that represent a class, a component, or a module, rather than looking at a 1,000 or 2,000 lines of code for a component or a module. Okay, so you will see immediately why is this module there, what is the purpose of that module, and why is it, and who is it communicating with. Okay, the communication of modules and packages are important because that's the way they pass parameters. One module calls another module, and they pass parameters between them. And so by having a package diagram or a component diagram, you will see what or how the different components or modules are cooperating or collaborating with each other to perform a function. So it's easier to understand what the lines of code are doing. Okay? So you would rather read um, pages of UML diagram than to read thousands and thousands of lines of code. Okay? And I already also mentioned, reading lines of code is not easy. Your own code that you have written last week, and you would read your own code, sometimes you would scratch your head and say, why did I do this? You forget, right? And so the difficulty is increased 100-fold if the code you are reading is not your own. Imagine reading source code that was written a year ago by another person. Okay? And you can just imagine the difficulty of reading code. Okay? And you will say, uh, why do I have to reuse the old code when I can begin from scratch again? Well, if you always do that for software, you will never move forward because every time you begin from scratch. So you never improve the software. Okay? So what happens? Software is thrown away. Years of development are thrown away because it can't be maintained. Okay? So that's wasted effort. And software is very important in today's application. There are faster and more big bandwidth, big computing power, but they will be of no use if software is not advancing from the current state. If every time you do is begin from scratch. You understand? Okay, you build on top of existing software and you add more features, more improved features and functions, and so software is moving up. And that is why we need to reuse software that was developed before. Okay. The design consists of the high-level design. Remember, we are talking about several um, um, ways of representing high-level design. And there are architectural styles that you can use. We have I've shown you the hierarchical decomposition or top-down. This is the most common architectural style. Okay, so you start from a box or a component or a package, and you decompose it into its component. You divide and conquer. Very important software process that we are using. And the hierarchical decomposition is used most often in architectural design. Okay? Layered architecture is either three tier or four tier. And this is also another common architectural style. That means you divide the different concerns of the project into its component. So, as we have discussed in the previous chapter, um, in the ISO OSI, the lowest layer is the physical electrical transmission of bits, and then The next layer is the assembly of the bits together in frames, and so on and so forth. So the in a three-layered three-tiered layered architecture, the lowest level is always the um, closest to the hardware. The second layer is the middle layer, and the third layer is the application. Okay, in the four tiered layered architecture, the storage is the lowest, or the lowest level is the storage. The two middle layers are the kind of in between the low level and the high level application, and then the top tier is the application itself. So there are others like repository, model view, MVC is very popular in web application, and we always use this when we have the chance, because this is well-defined architecture, and we begin or we design the architecture using three components: the model, view, and controller. Okay, and you follow this suggested architectural style when you are dealing with high-level design. Now, high-level design representation is always a component, package, or module, and they are not well defined yet. So it is like a high-level idea that you represent as a box. Okay? And you continually decompose a package, a module, or a component into its components, into its subcomponents. And you ask the question when you reach a particular level of module, package, or component, whether I can define it or I can decompose it into classes. And if you are able to decompose it into classes, then you are on the lower level design. So once you reach, you can represent the different parts of the software into class diagrams. That's when you begin low-level design. Okay, so the low-level design consists of class diagrams, and the class diagrams are contain member variables and member functions or methods, and that is defined for each component or package. If you are able to represent the next level of decomposition in terms of class diagrams or object diagrams, you have reached the low-level design level. Okay, and then the last level of design is called detailed design. So for each class that you have in the low-level design, you write the pseudocode of critical important functions. And the pseudocode represents the logic of that particular function. And once you have the low-level pseudocode or the detailed design in pseudocode, you have a means to actually check the logic of that method or function for errors, and if you find a problem or an error, it's easy to fix pseudocode. Once it is written in source code and there is a bug or a fault, you know very well, fixing source code is hard. Okay? And so you would like to spend more time in analyzing pseudocode than tracing the bug in a source code. Okay? That has proven to be a fact. Fixing the bugs in pseudocode is much easier than fixing the bug in source code. Okay, so before the source code is written, you write the pseudocode or algorithm of the method that would implement it. And so if you do that, you will hopefully you will spend less time in fixing bugs. Okay, so that is the format of the SRS. Okay, so we'll continue our lesson for today. Let's look at the chapter on systems design, addressing design goals. Okay. Um, Here in this example, you see here, we have the deployment diagram, and you all have deployment diagrams in your SRS. So it shows the hardware in two-dimensional boxes. The device is a Mac here, and this device here is a PC. And it's communicating with the Unix host a server, and the web server resides in that Unix host. And there is also another device here, and this contains the database. And the web server is connected to the database through JDBC, while the Mac and the PC are connected via HTTP. Now, we have noticed here that the Safari and the Explorer are the browsers residing in those Mac. So they are components, as you see here in the symbol. And on the Unix host, the web server is a software that you need to write. That's the application for the web server serving these two browsers. And there is support here by the database. The Unix host has a database. Okay, so what we do is we take this component and elaborate it. So we represent it as a web server software component, and inside the software component you have three classes, or three could be components or packages again. One is the servlet, the other is the HTTP service, and the other is the database proxy. And notice here the symbol, ball and socket. Ball is a provision that they can provide the service in this connection over here, and the socket here means I need a service from another component. So what this diagram is telling you is that from your deployment diagram, you can begin the hierarchical decomposition of your design. So using the hierarchical decomposition of web server, and the web server actually is detailed here into these three other components: servlet, HTTP service, and the database proxy. Now, if you will use MVC here, what will be inside the web server? Then the web server will be MVC, model, view, and controller. So you can have that inside this web server, and the model, view, and controller is already defined in Laravel. And Laravel, you can use the API Laravel, and you write your web server in PHP. So immediately you have the hierarchical decomposition of the web server into model, view, and controller, if the author chose to implement web server using the design pattern. Here, it's the decomposition of the web server consists of these three modules or components given here in this figure. Okay, so next is the another example of a design that that comes from the deployment diagram. Here in this deployment diagram, you have a device, an onboard computer, and a routing subsystem that you see over here. And on this device here, this could be the web host. This is an onboard computer in a car that helps. It's an application to actually give routing information to the driver, and a planning subsystem of how to plan your trip. Okay, so a hardware within a hardware that your car, your web host is a car, and inside the car you have a web server, an Apache web server, and there is a planning subsystem over here. So there are two software components given here, and the two software components have a routing subsystem here on an onboard computer, and a web server that has the planning subsystem. So right here on your on your deployment diagram, you can begin the high-level design of this application. And here you will have the hierarchical decomposition of the routing subsystem and the planning subsystem. Remember those two? Those two subsystems? They are deployment diagram that is given here. One is here, the planning subsystem, and the routing subsystem. Okay? Now, inside the routing subsystem, you have four decomposition of the routing subsystem. There is a route assistant, there is a location, there is a trip proxy, and there is a segment proxy. While the planning system consists of the trip, okay? So let us say you're driving and you you plan a trip to Alaska, and you're driving from San Bernardino all the way to Alaska. So you have a trip, a planning service, okay, because that's a long drive. What's your destination? Maybe your destination is Fairbanks, Alaska. You want to go there, yeah, from San Bernardino. Direction, you need direction. You have crossings and you have segment. So you divide your trip into segments. So the planning subsystem is divided into um, six components, and they are the the decomposition of the planning system, uh, uh, decomposed into six components, while the routing subsystem consists of four components, subcomponents. Now, if you can detail the route assistant, let us say the routing assistant needs to be developed, you can actually define here a class diagram that would implement the route assistant. If you can, then that's the beginning of the low-level design. And once you draw the class diagram of the route assistant, now you define or specify the important or critical methods inside that class that you will write the function or the method in terms of pseudocode. Now, another thing that happened here in this design is that you identify another subsystem called communication subsystem, which is not shown in the previous development diagram and deployment diagram. And all you see is a connection between the two hardware, the onboard computer and the web server in the car. And therefore, that is HTTP protocol, and you actually identify that as another subsystem called communication subsystem, and it has connection and message as the component of the these are subcomponents of the communication subsystem. So you have message and you have connection. Okay. Now, if connection, for instance, is still high level, that it is hard to detail it in terms of class diagram, then apply again hierarchical decomposition into this particular component. So again, decompose it into simpler components, and if the components becomes now a class, then you can detail the class through its class diagram with member functions. Okay? All right. Now, there is still two other supporting components that we need to include. So in addition to the communication subsystem, we also have map DB store subsystem. And another one is the trip file store subsystem. And this additional subsystem were identified because you want to implement persistent objects. So you want to store the previous trip file, that even though the car is shut down, the trip file store subsystem keeps a copy of the previous trip. So the previous trip is stored, and also the map is stored in there. So so in case the car shuts down, and the trip file store is stored, and the map database store is also stored in the storage system. Okay, so that's kind of a system design where your goal is to um, keep a, uh, a, a, a database or a service that provides advice on to go on driving trips. And um, hierarchical decomposition is very, very powerful in terms of design. I would suggest that you apply this to your projects and um, use your deployment diagram to begin your design. Identify the software that you will need to write to implement the to implement your software, and from the software part of the deployment diagram, you uh, uh, decompose each of these software components into each uh, components or parts, subparts of this big component. So, and the method is keep on decomposing uh, the component until you reach a level where the component can be completely identified through a class diagram. Okay, so hierarchical decomposition is what I would suggest that you do. Now, what happens uh, if the software you are continuing is doesn't follow this kind of architecture? Then you have to do a reverse engineering of the source code. I, you have no choice but to draw the uh, the software architecture and design based on the source code that you have. This is, of course, a big job, but it is important that you derive the software architecture and design from the existing software. Okay, and there is also another thing you can do is that you recode and um, try to fit or modify the code to follow your design. And of course, that's a bigger task to do, but it will help in terms of maintaining the software later on. I would first recommend reverse engineer the source code that you have. Try to determine the software architecture and design of the source code. And once you understand the software design, then maybe you can modify it to follow a better design uh, for future use. Okay? All right. Let's proceed to the. Oh, by the way, in the course of your hierarchical decomposition, you might discover some other component that were not there before. Like this, for instance, we identify routing subsystem and planning subsystem, and we have to add the communications subsystem, even though it doesn't appear in the deployment diagram. Okay, that is derived. Okay, these are design goals uh, that we need. And also, later on, because of the need for persistent objects, then we need to um, uh, add two other subsystems the trip file store subsystem, and the map database store subsystem. So these are additional uh, components that you need to support the entire application. Okay? All right. So um, there is a suggestion in the book regarding trade-offs between using a flat file for your storage management system, a relational database, and object-oriented database. So when should you use flat files? So you use flat files like an Excel spreadsheet or an Access database when you have voluminous data like images, and you have also temporary data or low information density like archival files and history files. Then the author suggests that you use flat files. But of course, there are problems with flat files because the flat files could have anomalies like duplicated information. And the search could be very slow because of the flat file. There is very little you can do in terms of indexing. And um, the index is, of course, one line of the address of that particular flat file. Now, you use a relational or object-oriented database if there is concurrent access. So if there are users that access it concurrently, then you need to synchronize their access so that you don't um, end up with data that is not correct, because you must guard against multiple simultaneous access, and it's unpredictable what the data would have after the multiple access. Access at finer levels of detail. So if there are very fine search in your data, flat file will be very slow to do that. Then or it may not be able to do it. Then you should choose a relational or an object-oriented database. If you're using multiple platforms or application for the same data, yeah, it also recommends relational or object-oriented database. A relational database, as you know, it contains several tables, so therefore it can handle complex queries. You are joining, you are trying to get information that was not there before, so you join tables to get more information than what was inputted into the database. And you have large data set. If the database is very large, then relational is better. And when should you use an object-oriented database? Extensive use of associations to retrieve data. And as you know, object-oriented diagram has a very nice diagram to represent class diagram. And class diagram is a UML or it's a standard conventional diagram in object-oriented approach. Medium-sized data set and irregular associations among objects. So you have object-oriented. But either way, I would say the choice is between relational versus flat files. That's the main choice of database today. Okay? So let me end my lecture here. I would like to Say be safe and healthy. I'll see you on Monday. I mean, Wednesday. Goodbye.